This split on the evolutionary tree between the non-avian theropod dinosaurs and their smaller cousins, the raptors, and the first birds, Archaeopteryx, can't be pinpointed in time. But the two groups, one that would never fly and one that would dominate the air, share many physical characteristics, including feathers.
The first sort of feathered dinosaurs that were clearly not birds were found around 1995. These fossils were coming out of China that had these really sort of halos of kind of feather fuzz around them, sort of very downy-like feathers. So it's not these asymmetrical, really modern feathers that most people are familiar with on birds.
More recently, Alan Turner made a discovery that extended this downy covering to more flightless theropod dinosaurs, velociraptors found in Mongolia.
This is the ulna of a velociraptor, so it's one of the lower limb bones, or the forelimb. And I found these bumps, these quill knobs along the back of the ulna, which is where the ligament that attaches the feather embeds itself in the bone. They're actually quite small, so I felt them actually before I saw them.
And these quill knobs can be found on modern birds.
What's interesting about Velociraptor is it's one of the larger of the dromaeosaurs known that we actually have direct fossil evidence for its feathers. We have good reason to have predicted that these animals would have been feathered because we know their earlier, smaller relatives had feathers.
Beyond cosmetics, these feathers are a further confirmation of the close connection between raptors and birds.
They're not just dinosaurs, but they're actually a particular kind of dinosaur. They're embedded in the tree of life within the group of predatory dinosaurs. They're in fact more closely related to things like Velociraptor than Velociraptor is related to something like Tyrannosaurus.
Though feathers are perhaps the most dramatic connection between raptors and birds, there are many similarities that are not just skin deep.
When you look at a bird today, a lot of what you see is in fact dinosaur and not as much bird as you think. The hollow bones are in fact a theropod feature. Those are around for 210 million years. The wishbone that you see within a bird, that's also a theropod feature, evolved long before flight ever evolved.
All those guys have, for example, a specialized wrist bone called a semilunic carpal. It does a big sort of flex motion like this, which in a predatory dinosaur is useful for grabbing prey. It is exactly the same motion that a bird does in their downstroke of a flight. And that's one of many, many anatomical characters that show us that birds are dinosaurs.
But why did these features lead to flight in some dinosaurs and not in others?
The whys of evolution are not an easy question for science to address because sometimes there may not be a why. It may just be sort of a happenstance of evolution that some of these features evolved and then happen to be advantageous. What we do know, at least about these features, is that they didn't evolve for flight, and they just happen to be able to kind of be utilized for that behavior in the earliest birds.
But if feathers appeared in raptors, for whom flight was an aerodynamic impossibility, did they serve some other purpose?
Right now, sort of the leading ideas about why feathers might have evolved have to do with their role in thermoregulation. Around the time that we see the first feathers showing up in the fossil record, within these group of dinosaurs, you're seeing a big shift from being a very big theropod like Allosaurus to going to be very small. So you're going from being multiple tons in mass to being maybe just 10 or 15 pounds. As you get smaller, it's much harder to maintain high body temperatures, and these are probably fairly active animals. And the evolution of feathers was somehow adaptive for maintaining body temperature as these animals got small evolutionarily.
Flight feathers were the last stages of feather evolution. Millions of years later, the evolution of the modern feather signaled the turning point from non-avian dinosaurs to Archaeopteryx, an animal that is recognizable as one of the earliest birds.
What we're looking at here are casts of the first and probably one of the best Archaeopteryx specimens found. These are preserved in very fine-grained limestones, and that preserve these impressions of the feathers that these animals had. What's probably most significant is all the things it doesn't have. You can look at its skull, and it still has teeth, just like all the other theropods do, but not like modern birds. So it really is this sort of kind of perfect transitionary animal.
Just as these prehistoric creatures were constantly evolving, our understanding of them is almost always changing as well. Two seemingly disparate disciplines, art and science, intersect to reveal just how much and how little we really know about these ancient monsters. Therizinosaurus clawed its way into the fossil record, literally. The first evidence of these freakish creatures, a giant 5-foot claw, was discovered in the late 1940s.
The first thing they found were a few claws from the hand, and they were so unlike anything we'd ever seen before that the scientist who named them thought that they belonged to a turtle.
When paleontologists discover any new creature, one of the first questions they ask is, what did it look like? Paleo artists like Patrick O'Brien, who illustrate for museums and publications, are instrumental in this fleshing out process.
So I'm picturing it must have been some truly huge prehistoric turtle with these giant claws on his 4 feet.
But the turtle connection proved to be a mistake. The claws were actually the first clues to the discovery of a bizarre new animal.
They began finding more and more pieces of more and more dinosaurs that were closely related to Therizinosaurus. So our image of what this animal was evolved a lot through time.
So it turned out to be a new and strange kind of theropod dinosaur, and not a turtle at all.
Therizinosaurus, who lived 70 to 75 million years ago during the Cretaceous period, was a theropod, a group of almost exclusively carnivorous dinosaurs that included T-Rex. But at 40 feet long and 3 to 6 tons, Therizinosaurus's body had some odd features: an extended neck, a beaked head, and a potbelly that are typical not of carnivores, but of herbivores. Scientists were baffled.
Therizinosaurs were an incredibly bizarre group of raptor dinosaurs. They weren't recognized as raptor dinosaurs for the first 50 years that they were discovered because they were so different from any other dinosaur we'd ever seen. The only way that the story got resolved was when we discovered exceptionally primitive forms. And those animals looked so much like raptor dinosaurs, but started to show some adaptations towards animals like Therizinosaurus that we were able to actually piece back the history and get at what the ancestry of these animals were.
The missing link in this mystery is on display at the Utah Museum of Natural History. Discovered in 2005, Falcarius is the most primitive specimen of the Therizinosaur group. It lived 130 million years ago and marks the transition between the predatory raptor ancestors and their plant-eating Therizinosaur descendants.
Falcarius still maintains a lot of anatomy that's similar to, say, Velociraptor. It still has a small body, powerful arms, but small claws. It is showing some changes that allow us to place it within Therizinosaurus. Its neck is starting to get longer, its head is starting to get longer. But basically, when you look at the skeleton of Falcarius, it's a raptor dinosaur with just a few changes that tell us that it just began to switch towards a new lifestyle.
Falcarius's leaf-shaped teeth are the most telling pieces of its anatomy that indicate it had begun eating plants.
The teeth are very well adapted for eating plants rather than eating meat.
These first steps towards herbivory grew more pronounced over millions of years of evolution.
There's about a 70 million year difference between Falcarius and Therizinosaurus. If you looked at the two of them side by side, you probably wouldn't recognize that they were closely related.
Therizinosaurus's huge size and bizarre shape make it a good candidate for a full-scale rendering. But rendering is an ambiguous process. Representations of dinosaurs must include the illustrator's best guesses of coloration, skin covering, and even behavior based on the scientific evidence.
On the computer, I created this drawing of a Therizinosaurus skull so that I could try out different soft tissues. First, I created an outline of the soft tissues with the muscles and skin, and then I thought I would try to sort of bird-like headgear, which is plausible on Therizinosaurus. They were feathered dinosaurs, and their relatives did evolve into birds. I also thought I would try to put more of a lizard-like headgear. This is exactly what modern-day iguanas have on the tops of their heads.
Artistic judgment and scientific judgment may not be as far apart as we think. In both processes, what we know about these long-extinct creatures is an approximation based on analogies and assumptions until definitive evidence is dug up that furthers knowledge.
Science is this ongoing intellectual pursuit, and that's kind of the beauty of it. You keep gathering data and keep putting forth these hypotheses and keep finding new lines of evidence.
All along the way, this is a self-correcting scientific process. We find better specimens. We often have to revise what we thought about animals, but that's fine. That's the way it's supposed to be.
There is fossil evidence that suggests features of Therizinosaurus's form and some behavioral surprises.
Most of the scientists think that Therizinosaurs probably had a beak because you can see that they have teeth in the skull, but only in this back part here for chewing, and in the front they don't have any teeth at all. So they probably had a beak that looked something like that.
Satisfied with these choices, Patrick begins to work with the whole animal. But the function of the massive claws is the thorniest issue.
Some people have suggested they use these for spearing fish, and the hypotheses kind of run wild. They may have been used to scare away predators. They don't appear to be very good for actual defense. They may have also been for sexual selection. They may have been a mating signal or just a sexy look for a therizinosaur.
Ultimately, Patrick's painted version incorporates the idea of the claws as food gatherers. Scientists theorize that Therizinosaurus may have pulled high vegetation down to its mouth to eat. He has also given the creature a potbelly, customary for animals that digest huge amounts of vegetation.
Plants are much harder to metabolize for animals than flesh is. Think of it, when you're eating a cow, you're turning a cow into human. That's kind of a smaller step than turning lettuce into a human. So it takes more time and more specialization than to be a herbivore. And one of the ways that herbivores deal with that issue is to have larger stomachs where they can leave the food in there longer to get more of the nutrients out of it.
Before the portrait is complete, Patrick must contend with one last detail that remains speculative.
Most of the fossils of the close relatives of Therizinosaurus were found with feather impressions in the dirt. And so it's assumed that Therizinosauruses were also feathered, and they were probably these sort of downy, sort of thin feathers. They weren't flight feathers. It certainly wasn't a flying creature.
And were the feathers brightly colored for display or muted for camouflage? Since we don't have any 70-million-year-old Therizinosaur feathers, color must be determined by deduction.
Therizinosaurs were very large. They probably weren't trying to bother to hide from anybody. So I'm going to guess that they're brightly colored with bright, bold patterns on them to impress other Therizinosaurs.
To work with extinct creatures, you have to accept that a certain amount of mystery will never go away.
It's all very speculative. Modern-day creatures do things that you would never guess just from looking at their anatomy. Modern-day whales, who can dive to such great depths for such long periods of time, if you only were looking at the bones of these animals and you knew something about mammals, you wouldn't guess that a mammal could do that, because mammals can't do that. They can't dive to such great depths and hold their breath for 10 minutes, 20 minutes at a time, and yet they do. So perhaps there were things like that the dinosaurs were doing that we just don't really know, and we just can't know. We probably will never know. That's looking pretty good.
Life on the ground